All right, 2.6. All right, section 2.6. We are going to be looking at what is called the chain rule and generalized product rule. All right, so before we get into actually how to apply this and what it is, I first want to do a comparison of a couple of functions. So we have dealt with functions such as this. And if I ask you to find the derivative of that function, it would be 2x. So we can do that. Now, what we're going to look at today is a function, and it's going to be slightly different. So here's your x squared plus 1, but now that binomial is raised to the 5th power. Let's close my blind over here. All right, so this is something we've not dealt with when we have 2 or more terms raised to a particular exponent. Okay, so I'm going to give you a little word referral to when looking at this. So this inside the parentheses, when your exponent is on the outside of the parentheses, this is going to be referred to as u. So we're going to take that whole binomial, x squared plus 1, and just substitute or call it u. Now, a way that you can look at this too, and you'll talk about, is this is kind of the junk inside of the parentheses. And purpose of using the word junk is because of the letter u there. So I'll say things like, don't forget to take the derivative of the junk, and you'll know what I'm talking about. All right, so with that as the setup, what we want to look at is what is called the generalized power rule. So again, we're taking the derivative, and we're going to have to learn this rule in order to correctly take the derivative when we have a function such as this. So it states if you have a function y equals u raised to the n. So in our case, our u is x squared plus 1. So that derivative is, again, you bring this in out front, so it's n times u raised to the n minus 1 times the derivative of what's inside the parentheses. So this is where I say, don't forget to take the derivative of the junk. That is what this is talking about right here. All right, so this is kind of the chain rule as well. So let me give you an example. So keep it where you can see that. Let's take our function f of x equals x squared plus 1 raised to the 5th power. And again, how do you know when to use this? When you have something that is 2 or more terms with an exponent on the outside of the parentheses. Okay, all right, so it starts out similar, and we're going to take this and put it in front. So the first derivative will be 5 times x squared plus 1 to the 5 minus 1, or 4, times the derivative of what's inside the parentheses. So that would be 5 times x squared plus 1 to the 4th power times, and now we're just going to apply our derivative rules to take the derivative of this, which would just be 2x. And this is a lot of times what students will forget to do. They'll do this part of the generalized power rule, but they will forget to take the derivative of the junk. All right, now, just to clean it up, this is all multiplication, so we can actually multiply 5 times 2x, so we would get 10x times x squared plus 1 raised to the 4th power. So this would be the first derivative. And that's all we're going to do is the first derivative of it. Okay. All right. Some examples that are a little bit more challenging. All right. So the function, but we're going to write this as y equals 100 times 7x squared plus 6 raised to the 10th power. And so I have a binomial all raised to the 10th power. So that tells me that I need to use this generalized power rule. Okay. So in order to find the derivative, we start out. So this 100, if you remember, that constant multiple just stays out front. I'm going to bring the 10 out front. 7x squared plus 6, and then 10 minus 1 is 9. And then don't forget to take the derivative of the junk. So I'm going to take the derivative of what's inside my parentheses, which will be 14x. Now, we want to clean it up a little bit. I can take 100 times 10, which is 1,000, and 1,000 times 14 would be 14,000. And then we have our x to the 7x squared plus 6 raised to the 9th. So not too bad. But what if I asked you to take the second derivative? All right. Things are going to get a little bit more complicated here because guess what? We have this times this. So we're going to have to apply the product rule. So I want you to think 1, 2, and don't forget that the product rule is 1d2 plus 2d1. So those don't go away. We have to keep applying them, okay? All right, let me move this up a little bit. All right, I want to be able to see that. All right, so we're going to take the second derivative. All right, so we're going to do 1. 1 is 14,000 x times the derivative of the second. Okay, so we are now going to apply the rule that we just learned. So first I'm going to bring the 9 out front. So I would have 9 times 7x squared plus 6. 9 minus 1 is 8. But then I have to also remember to take the derivative of the junk. So that's going to be 14x. Plus 2. So 2 is my 7x squared plus 6 raised to the 9th times the derivative of 1, which will just be 14,000. All right, so then what I'm going to do is I'm going to clean this up a little bit. So I'm going to multiply 14,000 times 9 times 14. And you get 1,764,000. And then we have x times x, which is x squared, times 7x squared plus 6 to the 8th, plus, and this is easier to clean up, all I'm going to do is put that 14,000 out front. Okay, now that is a sufficient answer for WebAssign. That would be a sufficient answer for the test. But just for what's coming in future chapters, I do want to show you that we could write this in a different form. And what I want you to look at or look for is the greatest common factor. So I want you to look at this as a term and this as a term and ask yourself, what do they share in common? All right, so the first thing I'm going to look at is 14,000 and this 1,764,000. Now, I don't know my multiples to get this, but because of this up here, I know 14,000 was in that. So I know 14,000 goes into both 14,000 and this number. So I'm going to factor out 14,000 because that's a part of my greatest common factor. Now this one has x squared, but this one does not. But they both have 7x squared plus 6. This one has 8 of them. This one has 9 of them. So I can factor out 8 of them. So what that leaves me with is, so where's my calculator? Here it is. All right, so 1,764,000, and I'm going to divide 14,000 into that. So I'm left with 126. So I factored 14,000 out of this, and I'm left with 126. That x squared did not get factored out, so it stays. This, all 8 of these got factored out. Plus, I'm factoring out the 14,000. And I'm factoring out 8 of these, which leaves me with 7x squared plus 6. And then let's see, these are both x squared. So I have 14,000 times 7x squared plus 6 raised to the 8th times 126 plus 7 is 133x squared plus 6. So this and this represent the same answer. And again, this is sufficient in WebAssign and for a test. So that one, especially taking the second derivative, we had to apply some additional rules. Okay. So we are going to apply what we've learned, but we are going to also add to it something that we did earlier in chapter 2. So let's say you are given the function f of x equals 3x plus 5 raised to the 4th power. And you are asked to find the tangent equation at x equals -2. Okay, so here's some things that we need to remember. Because it wants the tangent equation or the tangent line, we know that we are going to take the first derivative, but then we have to find that equation of a line. So we've done this before, but I wanted to do another example with applying this new derivative rule plus something that we have done in the past. So the first thing we're going to do is we're going to take the derivative of this. So 4 times 3x plus 5. 4 minus 1 is 3 times, don't forget to take the derivative of the junk. So I look at that, and that would just be 3. So that one's pretty easy. So I can multiply my 4 times 3, and I get 12 times 3x plus 5 raised to the third power. Okay, so the purpose of this is to get the tangent, or I'm sorry, this is the slope of your tangent line, because remember the first derivative is what gives us the slope. So I'm going to substitute in -2 to find out the slope of my line. So 12 times 3 times -2 plus 5 raised to the third power. So I can just put all of that into my calculator. I mean, of course, you can do, well, we could do this. This is -6 plus 1, or I'm sorry, plus 5, which is -1. -1 to the third power is -1. 12 times -1 is -12. So we can actually do that without our calculator. So this is the slope of your tangent line. So now to find the actual equation, recall that we need a point on the line. So I go back to my original function, and I'm going to find a point at x equals -2. Because remember, when we first learned, this is your point generator. This is your, point generator, slope generator. Okay, remember we talked about that. So I'm going to put in f of -2 would be 3 times -2 plus 5 raised to the fourth power. So this would be -6 plus 5 is -1, and -1 to the fourth power is +1. So this gives us the ordered pair -2, 1. And the reason we need that is because we need this and this. And we use point slope form. So I'm going to do y minus 1 equals -12 times x minus 2, -2 or plus 2, and I'm going to solve for y. So y minus 1 equals -12x minus 24. Add 1 to both sides, so y equals -12x minus 23. So this is the equation of the tangent line. Now, I do want to take a minute just to look at what the original function on Desmos, the point, and then this tangent, just because I always like to give you guys a visual of that. Whoops, I hit the wrong thing. Okay, so I've already put in the original function, and you can see that graphed right here. So next I'm going to put in the point that we generated, which was -2, 1. So then lastly is we're going to look at the equation of the tangent line, and it should go through this point right here. And we got y equals -12x minus 23. And sure enough, bam, there it goes. Okay? All right. A little bit more challenging generalized power rule derivative. We're going to do an example where we have to apply the quotient rule. So y equals 2x over x plus 1, all of that raised to the fifth power. Okay, so if you'll look inside at the junk, we're going to have to at some point apply the quotient rule. Now I want to remind you, this is low, this is high. And if you recall, we did low D high minus, whoops, that's supposed to be an H, high D low, all over low squared. All right, so just a reminder of that. All right, so we're first going to deal with this exponent on the outside. And so we're going to bring 5 to the front times what's in the parentheses, 2x over x plus 1. 5 minus 1 is 4 times, okay, now we have to apply the quotient rule and we have to find the derivative of the junk, okay? So this is where we're going to go low derivative of high, which would be 2, minus high, the derivative of low, which would be 1, all of that over low squared. All right, so then we're going to do some cleanup. So we have 5 times 2x over x plus 1 squared. And I'm going to distribute the 2. So we would have 2x plus 2 minus 2x, all of that, x plus 1 squared. Now, here's what's nice. That cancels that out. So in my cleanup, I am going to multiply my 5 times my 2, and this is like 5 over 1. So we have 10 over x plus 1 squared times 2x, x plus 1. Whoops, I don't know why that became squared. That should be to the 4th power. And this is to the 4th power. Sorry about that. All right, now, this is perfectly fine for an answer, all right? But some of y'all might recognize this x plus 1 squared, and we have an x plus 1 here. So I want to show you how you could rewrite this. So we've got the 10 over x plus 1 squared. I could raise 2x to the 4th, so it would be 2 to the 4th power, which is 16. X to the 4th power is x to the 4th. And then we would have this x plus 1 to the 4th power, which would then be 10 times 16 is 160, x to the 4th. And these are the same, so just add their exponents. X plus 1 to the 6th. So this and this represent the same thing. This is a little bit cleaner. That's why I kind of like it. Okay. All right. So now we're going to do a cost application problem. All right, so I'm going to give you a cost function, 6 plus the square root of 4x plus 4. Okay. All right, so this is the total cost in hundreds of dollars of producing X units of a product per week. Okay, so let's first talk about input and output. Okay, so we know that X is your input, and that would be the number of units. So producing X units. So my input X is number of units. And then your output is your cost. And again, if you got like 5, that would mean per hundreds. Okay. All right, so I'm gonna ask you, or you'll be asked to do 3 things. 1, find the cost of producing 60 units. B, find the cost of producing the 61st unit. And then we're going to actually do a little comparison to A and B. And then C, find the marginal cost at a production level of 60 units and interpret the results. Now, if you remember, marginal cost means take the derivative. And if you go back to that, what that marginal cost gives you is what is the cost to produce one more product. We've learned that in the past. Okay, so be sure that you can see this as I go down. It's going to be a little bit hard for me to show that on the paper as well, but you should have that in front of you. Okay, so part A says find the cost of producing 60 units. So I'm going to take the cost function and I'm going to substitute 60 in. So it'd be 6 plus the square root of 4 times 60 plus 4. So 6 plus the square root of 4 times 60 plus 4. And I don't want the rat. Oh, you can't even see that. Sorry about that. There we go. Trying to get that where you can see it. It gave me a radical answer, so I'm just going to push the double arrow and it'll convert it to a decimal. All right, so 21.6205. And then what you have to remember is this is per 100s. So that means I'd multiply it times 100. So what we get is $2,162.05 to produce 60 units. So 60 units would cost me this much to produce. Okay. Not $21, because that's what you got to remember. It's in hundreds. Okay, so part B says, all right, what would the cost be for 61 units? So instead of 60, I'm going to put in 61 and see what the total cost is. Let's see if I can get this where you can see it. So we would have 6 plus the square root of 4 times 61 plus 4. And I don't want the square root, so the double arrow. So I get 21.7480. And again, this is per hundreds. So I'm going to move this 2 places. So this would cost me $2,174.80. So what I want to look at is, here is producing 60 items. Here is producing 61 items. So what did it cost to produce that 61st item? Well, we could take the cost of 61 items minus the cost of 60 items, and we could find that. So $2,174.80 minus $2,162.05. So that 61st item costs $12.75. That's what that 61st item. Okay, so let's do part C. So part C, which we've done previously, is the marginal cost. So if you remember, the marginal cost means take the derivative of the cost, and this will tell you approximately what the next unit would cost. So if you produced one more unit, what would that approximately cost? So our answer should be something close to this. Doesn't mean it'll be exact, because if you recall, it was an approximation. So I'm going to rewrite the cost function just so we can see it. Now, it's the square root of 4x plus 4. But when I take the derivative, I don't want the radical. So I'm going to rewrite that as 4x plus 4 raised to the 1/2. We're going to have to use the generalized power rule. All right, so we're going to take the derivative. Now, because this plus is here, we're going to take the derivative of 6, which is just 0. Okay, if that plus wasn't there, then I would take 1/2 times that. But because that plus is there, you're taking the derivative of 6, which is 0. Now we're going to take the derivative of this. So this is where we bring that 1/2 to the front, times 4x plus 4. All right, now we're going to have to take 1/2 minus 1. So we did 1/2 minus 2 over 2, which is negative 1/2. And then don't forget to take the derivative of the junk. So the derivative of 4x plus 4 is just 4. And then I'm going to clean that up so I can multiply 1/2 times 4, which is 2, times 4x plus 4 raised to the negative 1/2. Now you can actually then put in 60 and do it like this. If you wanted to see that a little bit cleaner, it would be 2 over, because this is negative, so I'm going to bring it to the denominator. 1/2 is the square root of 4x plus 4. So these two mean the same thing. So I'm going to put in 60. Because then what we calculated would tell us approximately what the cost of the 61st item is. So I'm going to put it into this one. So we would have 2 over the square root of 4 times 60 plus 4. Calculator. So fraction 2 over the square root of 4 times 60 plus 4 equals, and we get 0.1280. But again, that's per hundreds. So we're going to move that 2 places, which would be $12.80. So it will cost approximately, $12.80 to produce one more unit. And this $12.80 is approximately the same as $12.75. So there you go. All right. Okay, there you go, 2.6.